once the student leaves. Thank you.
Goodbye.
Goodbye. Did we start recording yet?
Yeah.
Okay. Hit stop. Forces. Huh?
A force like in Star Wars?
Yeah, that was a funny joke. Okay, so we are moving on to forces and Sir Isaac Newton. Okay? The idea, so we're actually going past velocity, acceleration, and displacement. Believe it or not, we're moving on to new concepts. I know. So, Isaac Newton. Now the idea is really, this class is based on Isaac Newton. Yeah, Galileo had a hand in it, and we'll get down the road to some other people too. But really, this course is Isaac Newton's deal. And before Newton and Galileo, really the first scientist.
Sorry.
The first scientist was not really a scientist. It was Aristotle. Aristotle was not a scientist.
He was a philosopher.
He was a philosopher. Okay, but he figured that he could do all this reasoning, and come up with the right answers. Well, guess what? Most of those answers were wrong. Okay? When it came to science, at least. He would look at an object flying through the air, and that object would fall to the ground and stop. And Aristotle would say, this is an object, and this object stopped because it was supposed to. He said, any objects here on Earth are not supposed to move. So if you get it moving, it's going to stop sooner or later. It's not true. Okay? That was the concept. He said anything in the heavens, well, they keep moving because heavenly objects are supposed to keep moving. Okay? So Aristotle is not a scientist. And so what Isaac Newton's going to come up with has to first, so some of these concepts might seem pretty basic, but when you have been raised with Aristotle and his philosophy and his wrong reasoning, it was kind of a big deal to come up with the concepts he came up with. Okay, so he's going to publish a book, The Principia, and publish 3 laws of motion. Those are what we're going to cover right now, Newton's 3 laws of motion, which will basically be forces. Okay? But he published in a book called The Principia. Now, don't copy this down, but here's the first law. Like I just said, Aristotle would say an object is going to stop because it's not supposed to be moving in the first place. All right, what Isaac Newton will see an object, he sees that ball flying through the air, and he says, well, it falls down to the ground because of gravity, and when it hits the ground, it rolls to a stop because outside forces, because friction is going to stop it. Any outside force will act upon it until it's stopped. Okay? So it's a big difference. So we come up with the idea that objects should keep moving until an outside force acts on it. If I'm out in the far reaches of space and I throw a baseball 15 meters per second, that ball will travel 15 meters per second forever. Forever. It will keep going the same direction with the same velocity forever, or until some other outside force acts on it.
That would be forever.
Yes, that would be forever.
What if it like runs into the sun?
Yes, if it runs into the sun, that would be an outside force acting on it.
That would be
Okay, good. So, you'll see the statement, objects in motion stay in motion, objects at rest stay at rest. That's one, when my dad was in high school, this is one thing he remembered from physics class. So I put it up there. Okay, we're going to say it a little bit different than that. All right, we're going to say the law of inertia states that unless an outside force acts upon something, it will keep going with the same direction, the same velocity forever. Okay, we'll pause it here for station identification. Back. Good. Action. All right. Here's the next one. Don't copy down these word for word. I'll come up with the final slide for you to copy down. When an object is moving, what Isaac realized was this. I just realized I called him Isaac. I don't think I should. I'm not on a first name basis with Sir Isaac Newton. Anyway.
He's dead.
Everybody write that down. Now we know he's dead. Okay. If you apply a force, that does not give something velocity. It gives it acceleration. Okay? People think force is tied to velocity, how fast you go. And yeah, it would end up being that way, but it's with how much acceleration. So the more force you give something, the more it will accelerate. Okay? So, I push the stool along. Sound good? Okay? I give it a certain amount of force and it gets acceleration. Alright? Now, what about if I add mass to it? I give that same force. I apply the same amount of force, but I have somebody sit on top of it. Well, if I increase the mass, it's not going to accelerate as much. Okay? So force is directly proportional to acceleration. The more force I give, the more acceleration I'll get. Okay? Mass is indirectly proportional to acceleration. The more mass I put on the object, the more mass I try to push, the less acceleration I'll get out with that force. Okay? So he had to tie these all together. Again, don't copy this down. But the idea was that. Whoop. Okay? More force I give, more acceleration. More mass I give, less acceleration. Okay? So we tie those together, and we get that F equals ma. Force equals mass times acceleration. Now, there are actually other forces out there. So, I'm going to say net force. Okay? Because net force, there will be, if I push this chair, alright, I'm giving it an applied force. So I am giving it some kind of force there, but other forces might act against me. Friction, for instance, is acting against me. But whatever the net force is, after all said and done, the amount of force making this accelerate will be its mass times its acceleration. Okay? Think about your paycheck. You have your gross pay and your net pay. Okay? Your gross pay is everything before all the taxes are taken out, and then you have your net pay. Same thing with forces. You got to take away some force because there's friction acting on it, or whatever else. But the net force is, after all said and done, the amount of force to make it accelerate is mass times acceleration. Okay? All right. Don't worry about that. Here we go. Newton's third law. Don't copy this down yet. But for every force, there's an equal and opposite reactive force. Always, always, always. Okay? If I push down on this table, the table has to push back up on me. Okay? If it doesn't, I'd fall through the table like it was a ghost table. Okay? There's no such thing as a ghost table. So, if I push down, the table has to push back up. Always, always, always. But also if I move something, okay? Let me get a ball here. If I apply a force to the ball, okay, if I throw this ball and I apply 3 newtons as I'm throwing it across until I let go, okay, let's say I apply 3 newtons as it goes across. If I'm applying 3 newtons to the ball has to apply 3 newtons back at me. Always, always, always. Okay? Force is equal and opposite always. So not just when something's standing still, okay, but also when I'm moving something. Right now, I'm applying a force, it's applying a force back at me. Always. Okay? It's just that my mass is obviously more than the ball's mass, okay? And my feet are down holding me in place where the ball doesn't have anything to fight against it. So when I throw this ball, when I was throwing it during the throwing motion, okay, I applied 5 newtons of force one way, the ball was giving me a force back. Right now you're sitting in your chair. Your butt's giving a force on the chair's giving a force back up on you. That's why you feel the chair. Okay? Alright, so we call that equal and opposite forces. Oh, I guess that is the one. Okay, so equal and opposite forces is Newton's third law. And all it means is just look at the surface. Okay, don't get confused with everything else going on. When you look at that and say, well, there can't be equal and opposite forces because the ball is moving and you're not. If you look at the surface, where the 2 forces are being applied, there will always be equal and opposite forces. Always, always, always. If I push down on the table's pushing back up with me, or at me, with the same amount of force. Always, always, always. Equal and opposite. Okay? All right. Copy this picture, then let me explain it after. We'll pause here. Okay. I'm going to have slides coming up here to explain them all. I'm only going to talk really about these two right now, force applied and the force due to gravity. The rest of them we'll do another lecture on. Whenever we talk about forces, we want to be able to draw the vectors. Remember vectors? We had an arrow where we said the direction and the length of the arrow mattered, right? Well, same thing here. These are the vectors, and when we do a free body diagram, it just means draw a picture, okay, and draw all the forces on there with a vector. All right, we're always going to do that starting from the center of the object, so wherever the center of mass would be, we're just going to draw arrows. So instead of having arrows all over the place, they all start in the same spot. Okay? The two I just want to talk about today are the force applied and the force due to gravity, or the weight vector. Okay, and we'll talk about everything else later. This would be a picture here. Let me see. Here is what I just showed you up here. Here's this picture in action. Ready? Exciting, isn't it? Like that? Yep. There you go. Okay, I'll do it again. So, I'm applying a force. That would be the force applied. Okay? What do you think is fighting against me? What do you think that F sub F is? Going the opposite direction. Force of friction. All right. So force of friction is fighting against me, so I have to put it on there. Okay? What about F sub G?
Gravity.
Gravity. It's pointing down, right? The gravity is going to pull this object down. So another force acting on the object is gravity pulling it straight down. Okay, we'll talk about that more later. F sub n, capital N, means normal force, and we'll talk about that later. That's not net. That's something that we'll get into, but that's the normal force. Okay, so this object getting pushed along has the applied force, it has friction going the opposite direction, it has weight pulling down, and it has a normal force, which is really just the equal and opposite force. It's the table pushing back up on the object because it doesn't want to fall through like that ghost table. All right. So here we go. Applied force. There's not really much you can say about the applied force. It's the applied force. Whatever you push or pull with, that's it. All right. The force due to gravity, we're going to do F sub G. We also call this weight, though. All right. So the weight is, when you hear the word weight, that's different than pounds. It's going to be the weight, the force due to gravity, the force that that gravity is pulling down on it towards the center of the earth. All right? So weight is a force. The units for force, just so you know, will always be measured in newtons. Okay? Named after the Fig Newton. Yes, yeah, Isaac Newton. Yes, sir.
Oh, Fig Newton. Why is there like 3 equal signs for that?
That means defined as. Okay. So weight is a force. And we'll pause there. Go. All right. So weight is a force. You need to understand this. Weight and mass are 2 different things. Mass is how much matter you're made up of. Okay? Weight is how much gravity pulls down on that matter. Weight and mass are 2 separate things. You're going to be assessed on if you know the difference. And you're going to be assessed on being able to calculate weight from mass and mass from weight. It's very easy, but just so you know, that's what you need to understand the difference. Weight will always change depending on, well, it'll change if you're on another planet because weight has different, or has gravity to it, right? So if you're on another planet, if you have different gravity, your weight would be different. Your mass would never be different. It's how much particles you're made up of. All right? But weight is a force. So what would the units be for weight? Newtons. Okay? So weight is a force, so weight will always be measured in newtons. Here's the formula again. Weight is F sub g. When we do weight, we're going to write force due to gravity. That means weight. Okay?
So what is this equation? Mass times gravity equals weight?
Yep. What does little g stand for besides my rap name? Good. The number?
9.8.
9.8. So weight, force due to gravity is weight. That's equal to mass times gravity. Mass times 9.8. You're going to have to solve for one or the other. Okay, I'll say, what is the weight of this 50 kilogram wrestler? And you'll have to multiply by 9.8. Or I'll say, there is a 600 Newton object. What is the mass? And you divide by 9.8. It's that simple. It's from that formula. Okay? Alright, that is where I'm going to leave it for right now. I have a worksheet that you can do with just that information I've given you already. F equals ma and F sub g equals mg. Alright, we'll talk about the other forces, especially friction, which is a little trickier, next time.